Hey everyone, this is our first real lesson of the year, and today we're going to be talking about recognizing functions through tables. And if you remember back to Math 1, you learned about two different functions. You learned about the linear function and the exponential function. And you started off by looking at patterns and pictures and determining the number of boxes or something along that line in each sequence, in a sequence of events, and then you determine how many boxes were in there. You created maybe a table, and then you could tell whether it was linear or exponential. Well, this year, we are going to add to those two functions something called the quadratic, okay? So our objective today is to be able to determine what type of function is given by a data set. And the three functions, again, we are going to familiarize ourselves with is linear, exponential, and quadratic. Quadratic being the focus of Math 2. So if you remember how to create a table that represents the number of squares in each figure. So here's an example of that. Here in sequence 1, or in step 1, you can see that we have how many boxes? We have 3 boxes. In step 2, we have 5 boxes. In step 3, we have 7 boxes. And in step 4, we have 9 boxes. So what I'm going to do is I'm going to create a table of x, y values, I guess you could say. Okay, x, y values. And x is going to represent the step. And then y is going to represent how many boxes I have. So in the first step, I have 3 boxes. In the second step, I have 5 boxes. In the third step, I have 7 boxes. And in the fourth step, I have 9 boxes. So that is a table that was created based on the number of boxes in each step. Okay? Now, from here, we should be able to recognize the first differences. Well, the first differences are the same, and we'll talk about that shortly. But because the first differences are the same, we can say that the data represents a linear function. And we'll talk more about why it's called a linear function in another lesson. But for right now, what the first differences mean is that as the steps increase by 1 by a consistent amount, that the amount of boxes increases by a consistent amount. So we can see the difference between step 1 and step 2 is that we added 2 boxes. Okay? The difference between step 2 and step 3 is that we added 2 boxes. And the difference between step 3 and step 4 is that we added 2 boxes. So in each step, you can see that we are adding the same amount of boxes each time. This is called the first difference. Okay? The first difference. If the first differences are the same, this is a linear function. As I stated here, it represents a linear function because the first differences are the same. And that's something that you should have recalled from last year. So now let's take a look at another table or another set of pictures and create a table based on that. So if you would like to pause the video, go ahead and do that and create your own table. When you think you have it, go ahead and push play and see how you did. The goal is for each step is to figure out how many black triangles there are in each step. All right, so hopefully you paused the video and you went through this on your own. Let's go ahead and take a look at what you came up with. In the first step, we can see that we have one big black triangle. It doesn't say how big they have to be, it just says how many do you have. So in the first step, we have one black triangle. In the second step, you can see that we have 3 black triangles. In the third step, Well, we're just going to count them. We can see that we have 9 black triangles. Notice I'm not counting the upside down white triangle in between. I'm just counting how many black triangles I have. Okay. And then in the fourth step, we can sit there and count all of them, or we can do a little bit of math. We knew that this one had 9 black triangles, and it appears that we have 3 of those, 3 sets of those. So we have a total of 27 black triangles. Again, you can just count them all up if you need to. So from here, let's see if this is a linear function. Well, what we see, let's check our differences. Our first difference, the difference from step 1 to step 2, is that we added 2. Oh, that looks like it's the same from the first one, but really that doesn't matter what this number is. As long as it's the same, it's linear. Well, let's go ahead and take a look at step 2 to step 3. Well, we didn't go up by 2. We actually went up by 6. We added 6 to the set here. And then the difference from step 9 to step 27, we added 18. Okay, so we can see that the first differences are not the same. 2, 6, and 18 are not the same, whereas here it was 2, 2, 2. They're linear. But here it's not linear, so we can conclude, okay, it's not linear. So what is the other function that you know of right now? Well, the other function you know is the exponential function. So I'm going to recreate this table right here so we can look at a different type of pattern. We got 1, 2, 3, 4 steps. And in the first one we have 1, the second one we have 3, the third one we have 9, and the fourth one we have 27. So what kind of pattern do we see here? Because we definitely see a pattern in the pictures. What kind of pattern do we see in the table? Well, we don't see a consistent adding of numbers, but you might be able to see that how do I get from 1 to 3 in the same way that I get from 3 to 9, that I get from 9 to 27? Well, this is a matter of multiplication. So what did I do from 1 to 3? I multiplied by 3. What did I do from 3 to 9? I multiplied by 3. What do I do from 9 to 27? I multiply by 3. So you can see that it's not a first difference because we're not looking for how far apart they are. We're noticing that when we multiply one set by a constant number, we get the next step. Okay? So this is an exponential function, exponential. When you see you are multiplying by a common value to get from one step to the next step, and that value is the same in every case, that is an exponential function. So we say since the next number is determined by multiplying the previous number by a constant value, this data represents an exponential function. So we are multiplying by a constant value here. So those are 2 functions that you focused on last year. Let's go ahead and look at something else. Let's go ahead and take a look at something else. Let me move my graph paper down here. And just a side note, I'm sure I've mentioned this before, but it's going to be a very good idea that you take notes. You're going to want to take really good, consistent notes. Anytime you have notes or an example or statements in my lessons, you should take notes on those because you're going to submit that. Anytime it says explore or practice, you can do that on scratch paper, or you can do it on the backside of your notes or on a different page altogether. But I want to see a good, consistent notebook. And you're going to take pictures of each of your pages of notes and submit those as we go along. The other thing is, it's always a good idea to have graph paper in a math class. So if you could go out, if you don't have some already, go out and get a nice pad of graph paper that will help you out significantly, especially when we start graphing. All right, for this one, go ahead and pause the video and create your table, and then see if you can recognize whether it's linear or exponential, and then go ahead and push play to see where we go from here. So for this set of data, let's go ahead and create that table. And so we'll create our XY table. Again, the X represents the which figure or which step. So we have figure 1, figure 2, figure 3, and figure 4. And then the Y represents how many boxes we have in each step. So in figure 1, we have 1 box. In figure 2, we have 3 boxes. In figure 3, we have 6 boxes. And in figure 4, we have 10 boxes. So you can see that just by counting up. Now, what we're going to do is we're going to look for some sort of pattern here. Well, if we check our linear pattern, this one's pretty easy to see that it's not linear, because if I add, what do I have to add to get from step 1 to step 2? Well, I'd have to add 2. What would I have to add to get from step 3 to step 6? Well, I'd have to add 3. Since I'm adding 2 and then adding 3, I know it's not linear. I know it's not linear because the first differences are not the same. So let's take a look at exponential, because we're just checking to see if something makes sense. Well, what do I have to multiply by to get from 1 to 3? Well, I have to multiply by 3. What do I have to multiply to get from 3 to 6? I have to multiply by 2. Notice 3 times 2 is 6. So you can see right there it's not exponential because we are not multiplying by the same value. From 1 to 3, we have to multiply by 3. And from 3 to 6, we have to multiply by 2. Since those numbers aren't the same, we know it's not exponential. So what kind of function is this? And this is what's called a quadratic function. So the big thing is, how do we know it's quadratic? We'll get to what quadratic means in the future, but how do we know it's this thing called the quadratic? Well, the way we know a quadratic is we check our first differences. We can see that our first differences are up 2, we added 2, and then we added 3, and then we added 4. So we can see that yes, the first differences are not the same. But within the first differences, we see a pattern. It's not the same numbers, but can't you see that there's something going on here? 2, 3, 4. I bet you can guess the next number would be 5. Well, this is the second difference pattern. Notice what's the difference from 2 to 3? The difference from 2 to 3 is that we added 1. What's the difference from 3 to 4? Well, the difference is that we added 1. You can see here that the second differences, in this case, the second difference is the same. And so we would say that this is a quadratic function because the second differences are constant, okay? This data doesn't hold to a linear or exponential model because of the reasons we explained earlier. It actually follows a new pattern, and this new pattern, the second differences are the same. This is called a quadratic function. So now you have 3 functions that you should be familiar with, at least on a basic level. You have linear, when the first differences are the same. You have exponential, when you multiply by a constant number to get to the next value. And then we have quadratic, when you have the second differences the same here, okay? So let's go ahead and take notes on that. I'm going to go ahead and minimize my camera here so we can take good notes. Function types based on table change. We already kind of talked about this, but go ahead and write this down. This is very good, clear notes. A linear function is when we notice that the growth is constant. In other words, the first differences are the same. So if we look at an example of tables, we can see in this table, we can see that the steps are growing consistently, 1, 2, 3. What's happening from 5 to 3? Well, in this case, we're actually subtracting 2. And then from 3 to 1, we are subtracting 2. So it's a matter of addition, subtraction. Because those first differences are the same, we say that this is a linear function. For exponential, we would say exponential is a result of the growth happening as a result of a constant multiple. And so an example of this is as you see the x's increase constantly, we can see a pattern in the y values. Well, how do I get from 4 to 8? I add 4, but then from 8 to 16, I add 8. So you wouldn't say this is linear. Now, we could say it's quadratic with the pattern that we have right now. We would need more data. In fact, I should have added another one so we can see which one it is. But what I'm trying to get you to see is that, okay, well, I multiplied by what to get from 4 to 8? Well, I multiplied by 2. I multiplied by 2 to get from 8 to 16. So this could be an exponential model because the multiples are consistent. You can also argue, let's see, add 4. Yeah, you can't really argue that it's quadratic at this point because we don't have enough data. So we would say that this is exponential. For a quadratic, that is when, this is going to sound kind of weird the way I wrote this, the growth rate is constant. The first difference is what's called the rate of change. The rate here is constant. The growth is constant. The rate is a constant value. You're going to see in the quadratic that the rate is not a constant value. Instead, the second differences are the same, or in other words, the rate of the rate is consistent. So an example of this is 5, 7, 12, and that last number is 20 there. I know it's hard to see. But we can check our first differences here. Our first differences from 5 to 7 is up 2, and then from 7 to 12 is up 5, and from 7 to 20 is up 8, okay? So we can see that it's not linear. So let's go ahead and check our second differences. Well, our difference from 2 to 5 is up 3, and from 5 to 8 is up 3. So you can see that since the second differences are the same, then this is a quadratic function. Okay, so those are the three types of functions that we're going to work with. And again, quadratic is going to be our main focus throughout this year. So let's go ahead and get into a practice problem based on what you just learned. Let's see here. Identify what type of functions are represented by each table based on the patterns that you see. Is it linear, exponential, quadratic? So go ahead and take some time, pause the video, take some time and see what you come up with here. And then when you are ready with all three problems, go ahead and push play and see how you did. All right, for number one, I'm going to go ahead and write the table here. Number one, the XY table. I'm going to write it out so we can do some work with it. Step 1, 2, 3, 4. We have 64, 16, 4, and 1. So in this case, we have to ask ourselves, how do I get from 64 to 16? That's a big jump. And notice that jump, the difference from 64 to 16, is really big in comparison to the difference between 4 to 1. That's really small. So I know it's not going to be linear because those aren't going to be the same values. Do you see any other pattern? Well, how do I go from 64 to 16 to 4 to 1? Well, I notice that all of those are factors or multiples of 4. So if you notice this, you could say that from 64 to 16, you divided by 4, okay? Well, let's see if that's consistent going forward. From 16 to 4, oh, I also divided by 4. And then from 4 to 1, I also divided by 4. So we can see a consistency, but this is a consistency of division. Everything that we've talked about so far, linear, exponential, and quadratic, is all dealing with addition or subtraction and multiplication. So where does this division come from? It actually comes from the idea of fractions. What is another way of saying I divide by 4? Well, another way of saying I divide by 4 is multiplying by 1/4. Dividing by 4 and multiplying by 1/4 is the same operation. It's the same thing. So you can see here that to get from one step to the next, it's a matter of multiplication of a constant value or a constant number. This constant just happens to be a fraction. Don't get freaked out by that. That's just a reality. So this is going to be an exponential function because we are multiplying by a constant value. All right, for number two, we'll create that table so we can see it here. We have 1, 2, 3, and 4. We have 13, 10, 9, and 10. This is interesting. Well, it's not a matter of multiplication and division. I hope you can see that pretty well. It is because what do I have to multiply 13 by to get to 10? Well, I'd have to multiply it by, I have to divide it by something, some sort of fraction, but that fraction is not going to be consistent here. So let's check our first differences. Well, how do I get from 13 to 10? 13 to 10, I have to subtract 3. How do I get from 10 to 9? Well, I have to subtract 1. Oh, well, we know it's not linear because those aren't the same. Okay. Well, let's keep going because remember, there's this thing called quadratic. How do I get from 9 to 10? Well, I have to add 1. Well, that's interesting. I'm subtracting, and I'm adding. Let's check our second differences. How do I get from -3 to -1? On a number line, how do I get from -3 to -1? Well, I add 2. How do I get from -1 to 1? I add 2. Just think of a number line if you can't see that. If you can't see that on a number line, you're at -3. Let's see here. Okay. If I'm at -3, how do I get to -1? Well, I went to the right 2, so I added 2. How do I get from -1 to 1? Well, I added 2. So that's consistent. Since the second differences are the same, we would say that this is a quadratic function. And again, we'll get into what that graph looks like in the future here. All right, looks like I'm running out of notebook room. Let me go over here a little bit. Let's take a look at number 3. We have this table. 1, 2, 3, 4. And we have -4, 1, 6, and 11. Well, let's go ahead and check our first differences. And it's always a good idea to check your first differences first, and then check your multiplications second. So for this one, we're going to add 5. And then in this one, we're going to add 5. And then in this one, we're going to add 5. So we would say that this is linear. All right, so those are 3 good practice problems for you. Let's go ahead and take a look at one more slide. Another practice problem, okay? So create a table that represents the number of squares in each figure. Use the data in the table to identify what type of function models this situation best. So go ahead and pause the video and see what you come up with, and then come back when you think you have an answer. All right, for number 4, if we create our table, let's go ahead and create a data table here. We have 4 steps, and in the first step, we have 5. In the second step, we're going to have to add this up. We actually have 10. In the third step, we have, well, we can do some multiplication here. 3 times 5 is 15, plus these 2 is 17. And then the last one, it looks like we are 6 tall and 4 wide. So 6 times 4 is 24, plus 2 more is 26. All right, let's go ahead and check our first differences here. We notice that we're adding 5, then adding 7, then adding 9. Okay, it's not linear, but I notice a pattern in the first differences. To get from that first difference to that first difference, we add 2. And from here to here, we add 2. Since those are the same, the second differences are the same, we say that this is a quadratic function or quadratic relationship. All right, for number 5, we have step 1, step 2, step 3, step 4, and step 5. Look at that, we have a lot going on there. How many cubes in this case would we be looking at? Well, in the first one, we have 1 cube. Second one, we have 2 cubes. The third one, we have 4 cubes. The fifth one, we have 8 cubes. And then the last one, we have 16 cubes because 4 times 4. So let's go ahead and take a look at our first differences. We add 1, we add 2, we add 4, and then we add 8. Well, it's not linear, So let's take a look at our second differences. From 1 to 2, we went up 1. From 2 to 4, we went up 2. And from 4 to 8, we went up 4. Well, we can see that it's not quadratic because the second differences aren't the same. So it's not linear because these aren't the same. It's not quadratic because those aren't the same. So what does that mean? Well, that means that the only other option that we know of right now would be exponential, which means we have a matter of multiplication. So let's go ahead and verify that. We don't want to just guess it because it's the only option that we can think of, because there's a lot more in math that we don't know than what we do know. And so if we just guess based on the process of elimination, that's not going to work because there's a lot of other functions that you're going to learn throughout your math career. So let's check multiplication here. From 1 to 2, we would multiply by 2. From 2 to 4, we would multiply by 2. From 4 to 8, we would multiply by 2. And from 8 to 16, we would multiply by 2. So we can see that when we multiply a term, the number of boxes in the first term, we get, by a constant value, we get the next term. And so in fact, this is an exponential function or exponential relationship. All right, that wraps up this lesson. I hope you found it beneficial, and I hope that you learned a lot. If you have any questions, please feel free to reach out to me through email or through Zoom meeting or whatever it might be. Otherwise, go ahead and get the assignment done that's associated with this, and have a great day.